In this part of our chapter, we will be analyzing the bit error rate performance of basic binary one-shot modulation techniques in under additive white Gaussian noise, in the additive white Gaussian noise channel, which we abbreviate as the AWGN channel. Now, the model is somehow we have received this signal R of t, which contains a pulse, a message waveform that, one of the message waveforms that we have, characterized in the previous lectures. For example, the mth waveform, m being 1 or 2, randomly chosen, plus additive white Gaussian noise. So n of t denotes a sample function, a realization taken from a Gaussian process with flat power spectral density equal to and not over 2 watt per hertz. So this is the model. Signal plus noise forms the received signal. Okay. Now, what is the goal of the receiver? The goal of the receiver is not only to demodulate, as we were doing in analog modulation, but to detect after demodulation. Detect whether a 0 or 1 was sent. In general, in M-array communication, we do not only detect whether a 0 or 1 was sent, we detect which bit sequence was sent. But now we're focusing on the binary case, so we will detect whether a 0 or a 1 was sent. Okay, the goal is to process the received signal, the received waveform R of t in the bit interval, okay, to recover the bit that was sent with minimum probability of making an error. Okay. Now, it can be shown that we can subdivide this receiving process in terms of a demodulator and detector without any loss, because we know a way of doing this to provide what is called a sufficient statistic for making this decision with minimum probability of error. Okay, now the demodulator is going to obtain this vector y, which is going to be the sufficient statistic. Okay, and the detector will then take a look at the vector y and decide which of the waveforms, in this case, which of the 2 waveforms, because we're talking about the binary case, which of the 2 waveforms was sent based on the observation of the sufficient statistic y. So the demodulator is going to produce this y. Okay, y can be a scalar or it can be vector valued. In the case that it is, whether it's a binary, a binary antipodal or binary orthogonal signaling scheme, whether y is a scalar or a vector is going to change. Now, this process of demodulation without loss of information, that is to produce a sufficient statistic, we will see 2 ways of doing this, which are equivalent. The first is a correlation type demodulator, and the other is going to be called a matched filter. Now, correlation type demodulator works as the following. Now, first consider binary antipodal signals, for example, binary, that's resulting from binary PAM. Okay, we have S1 or S2 multiplied by a pulse, basic pulse, unit energy pulse phi of t. Okay, So the received signal is either square root of 2, I'm sorry, either square root of EB times phi plus noise, or negative square root of EB times phi plus noise. Okay, so how can we, detect? Well, we use this cross correlator first in order to form this Y. How does this work? Take the received signal and correlate it with the basic pulse shape phi of tau, the basis function phi of t. So r of tau, phi of tau integrated from 0 to t. And then sample the result at the end of the bit interval, TB. Okay, so when we write the received signal R of t, okay, the correlation, the cross correlator result is going to be Sm times the phi squared d tau integrated from 0 to t times the noise times phi of t integrated from 0 to t. When we consider this at t equals tb, what do you see? Well, the energy from 0 to tb is 1 for this unit basis function phi of t. So the result is going to be Sm plus n, where n is the filtered noise. Okay, n is a noise term that comes from taking this white Gaussian noise and passing through a linear operation. But you know that when we have a Gaussian random process, when we pass it through a linear operation like this, the result is a Gaussian random variable. Okay, so n is Gaussian. Okay. It is also zero mean because the original process is zero mean. What is the variance of this random variable? Let's compute that. The variance of the random variable n is, since it's zero mean, it's also equal to the expectation of n squared. But when you write n squared in terms of what n is here, well, we can bring the expectation inside the integration, and we can realize that phi is deterministic, so it comes out of the expectation. So we end up finding expectation of n of t, n of tau, phi of t, phi of tau, dt, d tau. Okay, but notice that this is white noise. So this expectation of n of t, n of tau is delta t minus tau times n naught over 2. Remember, the power spectral density is simply n naught over 2. So the corresponding autocorrelation is n naught over 2 times delta t minus tau. Okay, so then we use the shifting property of the delta function to find that this integral is equal to n naught over 2. Isn't this fascinating? I mean, this is one thing that is neat about all of these definitions, such that it brought to us a white Gaussian noise process with power spectral density n naught over 2 in the form of a scalar Gaussian noise, additive Gaussian noise component of variance n naught over 2 at the end of our cross correlator. So at the input to our detector, we have a scalar plus noise. The value of the scalar is either, well, in the antipodal case, square root of EB or negative square root of EB. And n, the value of this noise n, is exactly equal to m naught over 2, which is our power spectral density. I think it's pretty neat. Okay, so now we're going to make a detection based on this Sn plus Sm plus n. In other words, we're going to make a decision as to whether they sent us a 0 or a 1. In other words, we're going to try to infer whether Sm that they sent to us was square root of EB or negative square root of EB. Okay, if there was no noise, this would be trivial. But the noise, if it turns out to be large, it can corrupt the signal such that we can mistake a square root of EB for a negative square root of EB, etc. What are the chances that this will happen? Well, let's see the probability density function of y. We are going to look at the probability density function of y under the condition that Sm was sent. In other words, as you know, this is the conditional probability density function, condition on the signal that is sent being equal to Sm or S1 or S2, right? So in general, if Sm is sent, what is the conditional density of the detector output, the correlator, I'm sorry, output y? Okay, so notice that y is Sm plus the noise. And this is Gaussian with mean 0, variance m naught over 2. Okay, so when I shift a Gaussian, so this is a constant. It is either equal to square root of EB or negative square root of EB. You know very well that when you take a Gaussian and add a constant to it, the PDF gets shifted such that it is centered around that constant rather than being centered around 0. So if S1 is sent, okay, y is equal to S1 plus and not over 2. In other words, square root of EB plus, I'm sorry, I'm not over 2. It's n. Square root of EB plus n. And n is white Gaussian noise, 0 mean. So the resulting conditional probability density function under the condition that S1 is sent is going to be this. If N2 was sent, y is negative square root of EB plus n. So the conditional PDF under the condition that S2 is sent is going to be centered around negative EB over 2. All right. Now, we have y, and we need to decide on whether S1 or S2 is sent. What is the criterion for this decision? We want to minimize the error probability. We want to minimize the probability of deciding on the wrong hypothesis. Okay, so it is a so-called hypothesis testing problem. All right. By the way, as a note, notice that we have used this correlator. We have used integration, and then we've taken a sample at the end of the integration. But an integrator must be used with care because an integrator has memory. Okay, so essentially we need to ensure that we reset the integral result to 0 at the end of every sampling interval. This is called integrate and dump. Okay, it's called integrate and dump filter. Okay. All right. Before we go on to analyze the probability of error, let's see the operation of this correlator followed by sampling on two examples. So consider these two signals. Notice that S2 is negative S1, so this is binary antipodal signaling. So notice that the correlator output is taking S1 multiplied by phi1 and integrating from 0 to t. Okay, what is phi1? Phi1 is a scaled version of S1 in this case. Do you remember what phi1 is? Let's try to sketch it here. Square root of 1 over TB. Let's see. Right. And when we multiply.
Hocam kök 2 bölü TB olmayacak mı?
2 over TB, you may be right. Yes, you're right. Square root of 2 over TB. Now consider multiplying these two things and integrating. What we will find is the integral is going to keep increasing because the product is always positive. It will keep increasing and it will increase up to square root of TB at square root of EB at the point TB. So at time TB, the integral is going to reach its maximum value. This is no coincidence because this is this is why the correlator is an optimal demodulator. Okay, we will talk about the optimality of a correlator later on. At the moment, I'm just giving you what it is without giving you the why or why it's optimal. In the case that S2 is sent, when we multiply by gamma 1, the result is going to be always negative. And when we integrate, the integral is going to make a negative peak at the value TB. So when we sample at TB, ideally, we're going to get either square root of EB or negative square root of EB under no noise. Of course, when there is noise, we will get square root of EB or negative square root of EB plus noise. Okay. Now, this thing can be done in discrete time. Suppose R of t was sampled at intervals of, for example, bit interval divided by 20. Okay, then we would be having this discrete time integration, which is summation of sampled values of R multiplied by the sampled values of the basis function. And again, the correlator output is going to peak at TB, whether it's positive or negative, it's going to make a peak. Okay. Now, this is for antipodal signals. Okay. Now, how about for orthogonal signals? For example, PPM, pulse position modulation. if we passed it through a correlator. Now, first of all, notice that in the orthogonal signaling case, we have not only one, but two basis functions. Okay. So, and these basis functions are orthonormal. So, in this case, it is optimal to cross-correlate the received signal with both basis functions and obtain a two-dimensional correlator output. That is, have two branches. Take the received signal, correlate it with phi1, sample the result, correlate it with phi2, sample the result, and we have a demodulator output in the form of a vector with two entries. Okay. So how do we use this to detect? Okay. Suppose the transmitted signal is S1 of t, okay, which is S11 gamma 1. Okay. The output of the first correlator is going to be S11 gamma 1 plus noise multiplied by gamma 1, I'm sorry, not gamma, phi 1, okay? So it is going to be S11 plus N1, okay? But S11 is square root of EB, okay? Square root of EB plus N1, okay? Where the noise component is again AWGN. The output of the second correlator is just going to be noise, okay? Because, you know, take the signal, pass it through the second correlator. By the orthogonality of phi1 and phi2, we're going to have this term being 0, and we're going to have just noise coming out of that correlator. So, when you have orthogonal signals, the received signal vector, when S1 is transmitted, is going to be energy plus noise and noise. Okay, so you'll receive energy along one basis function, just noise along the other basis function. Okay, so now we're talking about two different correlator outputs. If S1 is sent, the first correlator output, under the condition is that S1 is sent, is going to be noise plus a value, positive value. So it's going to be centered around EB. The second correlator output, given that S1 is sent, is going to be just noise. Okay, so the probability density function is going to be centered around 0. Okay, so under, basically, let me repeat, under the condition that S1 is sent, given S1 is sent, we have Y1 and Y2. Y1 is going to have a probability density function that is centered at EB. Y2 is going to have a probability density function that is centered at 0. Notice that N1 and N2, the noise outputs of the two branches are uncorrelated. Why? Because the original white Gaussian noise, the original noise is white Gaussian, right? So if you if you take samples from Gaussian noise process that is white, you will find that they're uncorrelated. Simply if you form linear combinations of these samples, they're going to be uncorrelated. So because of this reason, since N1 and N2 are two filtered versions of this white Gaussian noise process, they're going to be white, but you can, I'm sorry, uncorrelated, but you can see it simply from writing the cross correlation. Again, phi1 and phi2 are deterministic, so the expectation is only over n of t and n of tau, and we know that the process is white, so n naught over 2 times the delta function. And because of the shifting property of the delta function, we end up getting reduced to, getting rid of one of the integrals. And since phi1 and phi2 are orthogonal, the result is 0. Okay, now N1 and N2 thus are uncorrelated. As they're also Gaussian, they are independent. Okay. Now, so basically, again, let's emphasize this fact. The independence of these terms, N1 and N2, independence of the noise terms at the correlator outputs, are because of the orthogonality of the basis functions phi1 and phi2. Okay. Let's repeat. When I take samples from a Gaussian process, they are Gaussian and jointly Gaussian. And when I form this cross correlation, I realize that since the process is white, n of t and n of tau have a, so basically the process has an autocorrelation function, which is a delta function. Okay. And since even in that case, if phi1 and phi2 were not orthogonal, we would have n1 and n2 being correlated. However, as phi1 and phi2 are orthogonal, the correlator result is 0. So N1 and N2 are uncorrelated. Because they're Gaussian, they're also independent. Okay. Now, when S2 is transmitted, so far we were focusing on S1. When S2 is transmitted, the first correlator output is going to be simply noise. The second correlator output is going to be noise plus energy, or noise plus a scalar term, square root of EB. So now the conditional joint PDF of S1 and S2, what is that going to be? We already proved that the noise terms are independent, and the noise terms are the only thing that is random here. So we can find the joint conditional PDF by multiplying the individual conditional PDFs, right? When S1 is transmitted, remember, Y2 is simply noise. Y2 is equal to N2, and Y1 is equal to square root of EB plus N1. But N1 and N2 are conditionally independent, conditioned on S1. So under this condition that S1 is transmitted, N1 and N2 are independent. So we can find the joint conditional density by multiplying the individual conditional densities. The conditional density of N2 is very simple. Okay. I mean, simple, it's not this. We should write it down. So remember, N2 and 2 is Gaussian with mean 0, variance and not over 2. Okay, the PDF, so under the condition, this is all under the condition that S1 is set. The conditional PDF of Y2 given S1 is then 1 over square root of 2 pi and not over 2 e to the minus Y2 squared over 2 and not over 2. Why? Because it's 0 mean. So let's simplify things. 1 over square root of pi and not e to the minus Y2 squared over and not. Okay. How about if Y1 given S1? It is similar, except now it's not a 0 mean random variable. It has mean square root of EB. So 1 over square root of pi and not e to the minus Y1 minus square root of EB squared over and not. So now, when I multiply Fy given S1 and Fy1 given S1 and Fy2 given S1, I find this expression. This is under the condition that S1 is transmitted. By symmetry, under the condition that S2 is transmitted, we find this expression where the roles of Y1 and Y2 are now reversed. Okay. Now, next time, we will talk about the matched filter as demodulator. I will introduce you the matched filter and prove the optimality of why it is an optimal demodulator that provides for us a sufficient statistic for optimal detection. And we'll see that it is equivalent to the correlator. And then we will go on to compute the bit error probability at the end of the matched filtering or at the end of the correlation and sampling operation for both antipodal and orthogonal signaling mechanisms.